Hello. It's a pleasure to have the quantum session within the Supercomputing Asia event here in Singapore. My name is José Ignacio Latorre. I'm the director of the Center for Quantum Technologies in Singapore, and I will be moderating this event. Before starting with our first speaker, I would like to bring to the audience a number of news that have appeared in the last year or the last couple of years. So the big first piece of news is that quantum computing is progressing. So we do have very important technical progress in the field of quantum computation. Remember that everything is about controlling matter at on unprecedented level. So we want to manipulate individual atoms, individual photons, individual elements, ions, or superconducting currents. We want to manipulate states of matter which are not obvious, that bring up all the quantum properties that nature has hidden there. So in particular, I would like to go through the planet and say a few of these things. First is North America, and indeed, we have seen this year a number of announcements of new devices, new computers. Let me mention in particular AngelQ, or Rigetti, or IBM, or D-Wave, or other platforms like Xanadu or PsiQuantum that also bring an enormous progress to the field. This year is like the first year that really we see changes which are relevant in Europe. My first congratulations is for IQM, where they have opened for the first time a 5-qubit machine as a commercial product, and this is really good news. We also will have shortly an announcement by Open SuperQ. We have startups like Alpine, like Pascal, like Kilimanjaro, that are bringing new competitiveness to the whole continent. There are places like Delft in the Netherlands, which is simply a very impressive site for the development of quantum technologies. Of course, we have quantum developments in many other places. In particular, let me mention Singapore, where we have made an agreement to have a first quantum computer for production sitting at the National Supercomputing Center within the quantum engineering program. We will also have efforts in middleware, and we will have efforts in software. Singapore also has startups that are progressing steadily, and later we will have a panel with those startups in Singapore. And other countries are also making amazing jumps. So we are seeing national plans, quantum plans in different places, like in Israel. Recently, during the last 2 years, we had the French plan, we have the German plan, we have now a Spanish plan coming. Other countries, like I said previously, Netherlands or Austria, have been extremely well positioned in this race. We see also developments in countries like the Emirates, and very likely this will pervade the planet. Okay. The second piece of news that I would like to bring to the community is the fact that although everybody talks about quantum computers, the economy is much richer than that. So we should think of a quantum ecosystem which is being developed. And that includes what the label I like to use is enabling technologies. And we will see a lot of that coming in the next years. We will see the economy based on producing elements necessary for quantum computing, but themselves, they are of different kinds. We have fridges to go down to low temperatures, so cryogenics. We have cables to work in this regime, or we will have fast electronics to control these machines. Again, let me mention explicitly two countries. One is the Netherlands, has an enormous amount of effort on enabling technologies, and another one which is pushing very strongly this idea, two more. One is Finland, and the other is Israel. Okay, so we are seeing that the quantum economy is far more than just a quantum computer. Okay, there are plenty of pieces of the industry that can come and merge. So there is another and final remark. I don't want to use a lot of time, which is related to this question: where will we have quantum computers? Okay, so this is a non-trivial question. If we look now at the most powerful classical computers, where are they sitting? Well, we have supercomputing centers. So we have a very large power of classical computation in corporations and companies, but there are places where you have the ultimate level of computing power, which is the supercomputing centers. So if we are now building machines which are supposedly to be even more powerful than the classical machines, and they can address certain problems in an amazing way, where are these machines gonna to be put? So it is just natural to think that there will be an intimate relation between quantum computation and supercomputing centers. And this is what is being done in different countries in the planet. And I give first the example of Singapore, that indeed, under the quantum engineering program, a production quantum computer will be sitting at the National Supercomputing Center. But Europe has devised the so-called Euro HPC program, and now there is HPC plus QCS, Quantum Computer and Simulation. There is now a white paper, and there it is explicitly discussed how all the supercomputing centers in Europe should have a quantum computer. And there will be a coming call in this spring for the first two of these machines to be sitting in supercomputing centers. The same strategy that I've illustrated with Singapore and with Europe will be pervading the planet, in my opinion. Japan is already having an effort in joining quantum computation with supercomputers at RIKEN. So without further ado, let me start the session. And our first speaker, it's Professor Rainer Dumke, who is at the Center for Quantum Technologies and at the NTU, Nanyang Technical University. Professor Rainer has a lot of experience in quantum technologies, including quantum computation, but also quantum sensing, gravimeters, and also the control of matter at an amazing level, such as having the field of atomtronics. So Rainer is responsible for the future first quantum computer for production in Singapore, and we would love to hear from here his ideas. Rainer?
Okay, thank you. Thank you for the nice introduction, and it's a pleasure to be able to talk at this conference. Especially, it's not a typical physics conference; it's actually a conference on on supercomputing, not necessarily superconducting. Okay, so what I would like to talk about is about, let's say, the hardware perspective of quantum computing. Of course, let's say this, what I will talk about is actually done by a large group of researchers involved in this progress, which are listed here in my group. And then we also have, of course, collaborations with our partners from overseas. And this is, let's say, a decent effort or large effort where we actually try to build, let's say, the infrastructure to, or we're building the infrastructure to develop quantum hardware. For actually putting it then, as Ignacio was saying, it into a production quantum computer which can be housed within a Singapore supercomputing center. Okay, so maybe let's go to the next slide. Down here. Okay, so it's I think fair to say that the, let's say, current bottleneck in quantum computing or progressive quantum computing is actually the hardware. So this is actually also where we are focusing on. We actually build right now, let's say, a test bed for researching on, let's say, various fronts in, let's say, quantum hardware for quantum computing. And this test bed actually is or will be open access. So let's say other groups, collaborators can actually also use it and also control part of it from overseas or wherever they are. And this test bed, we can actually characterize various solutions ranging from, let's say, cryo-CMOS integration, maybe cryogenic FPGAs, certain amplifiers, and even, let's say, look further to future integration with, let's say, other quantum systems. So the system we have, let's say, in the last year, we started with the 2-qubit system. Now we are in this year scaling up to 10-qubit architecture. And let's say in future actually would like to go further to actually even more versatile processors, which can be then also implemented in our platform. To give you an overview of sorry, I have to go back in slides. Okay, no. To give you an overview of the schematic architecture, which is shown here, you can actually see this has, let's say, various parts in it. So right now, the system can be accessed via an API on the cloud from a user from anywhere actually in the world, where actually he can upload some abstract quantum circuits or even just certain, let's say, microwave byte sequences you would like to, let's say, play on our system. Then at the same time, there's also a database where we can actually, or we restore results which we actually receive from the, let's say, experiment, which then also the user has access to. We can actually do this because, let's say, our local worker PC has an executor on it, which is, let's say, with well-defined commands, so that it's let's say safe to expose the system to, let's say, to the outside, to the cloud. In the future, actually, we will progress further to interface the system with the Qibo framework in order to automate further the process of the circuit execution. I think Stefano will talk about the Qibo project later, can learn a bit more about this. Then, let's say, in our lab side, what we have is, let's say, a structure which is within the worker PC. So there we get, let's say, the data from the cloud and translate it to, if it's, let's say, a certain circuit, we translate it into pulse arrays or certain waveform arrays, which we upload to via network switch to an array of FPGAs. And also we get actually the data from the FPGA array and the raw measurement data and extract certain information out of this, which we can then send up again to the cloud, accessible for the user. For example, we can determine the phase and amplitude of the qubit states, or to determine the qubit states. Then on the very low level, we have actually the FPGA array. And this is, let's say, where we bridge more or less the classical world to the quantum world, one could say. Here we actually generate this microwave pipe strains directly from the waveforms which we receive from the worker PC. We also read out this microwave pipe strains and then store it on the worker PC as well. What we also have is a feedback between the ADC and the DSC directly on the FPGA, so that depending actually on the measurement on the ADC with some hardware overhead, depending on the measurement with the ADC, we can actually change, for example, the waveforms which are streamed out to the quantum circuit within an extremely short time scales of about a few hundred nanoseconds. This is, let's say, interesting for a little bit more future quantum codes, or also for potential applications in error correction. Let's zoom a little bit into the setup of the FPGAs. So we actually have there an RFSoC FPGA from Xilinx. And the, or let's say it's one let's say unit. We have several units in parallel. It has actually 16 DSC channels and 16 ADC channels. All of these channels are synchronized, so they stream out the waveforms exactly in phase. And what is also very interesting is that they support higher Nyquist zones. So with the sampling rate which we have, was about 6 gigahertz, we can actually directly generate the signal on the FPGA. There's no need for additional mixers down the road. And also we have integrated some feedback systems with some hardware overhead. We can actually direct feedback depending on the measurement what the DSC is actually streaming out. This diagram shows an overview of how this FPGA systems is actually laid out. So we have this FPGA areas, FPGA 1, 2, and so on and so forth, which have integrated the DSCs and ADCs. The data from this FPGA towards the FPGAs is streamed from from this local worker PC via the network switch. What's also, let's say, extremely important is that we have a master oscillator, a clock system, which syncs all FPGA to an external clock, so that we make sure that the FPGAs are actually working on the exactly same clock cycles. For this, what we also have to do is, when we actually start the FPGAs, they actually have to receive the trigger signal exactly at the same time, and also exactly synced with the clock cycles. For this, actually, we start, or let's say we have a trigger source on the PC, which is then fed to a D flip-flop, which actually syncs the trigger of the PC with the clock cycle. So it's always coming to the exact phase of the clock cycles to the FPGA. Okay. Additionally, we have developed current sources in-house, extremely stable current sources, which are actually used to bias the qubits. Right. So this gives you an overview of the, let's say, low-level electronics which we have implemented. Then, of course, after this FPGA system, we also have, let's say, the signals will be sent to the dilution refrigerator, in which we have our quantum processor. In the past, we had, let's say, 2-qubit system in a 3D cavity, which actually was produced in-house, where we can actually demonstrate the, let's say, various types of gates entangling this qubits. And we also have demonstrated, let's say, small code, Gaussian factorization on a single qubit system. So this gives you sort of the overview that, let's say, with this setup, we are already able to, let's say, manage, let's say, low or small number of qubits. And the idea now is actually to go to larger systems, in this case, as intermediate step to a 10-qubit quantum processor, which then also will be within this year integrated into our system and will be also accessible to the outside. However, if these are, let's say, decent intermediate goals, which are fairly, let's say, straightforward in principle to achieve. It's just some engineering. To be, let's say, a little bit more futuristic, the question is actually, what will be next? So one of the big problems we are facing, of course, is that we don't have a very good quantum memory. As you actually may know, superconducting qubits, they usually have coherence times in the range of tens of microseconds, maybe 100 microseconds. And we can't really store, let's say, quantum information on these systems for a long time. It's also very problematic to actually let the, let's say, various quantum processors communicate with each other on a quantum mechanical level. Because it's, let's say, typically the superconducting qubits are working in a microwave regime, and sending, let's say, single microwave photons over 300K environment is actually not possible because they will be buried by the thermal noise, and we can't detect this or we can't distinguish the single photons from the thermal noise. So what potential avenues to overcome this in future might be there? We are actually exploring the coupling of, this more on the research side, the coupling of, let's say, superconducting qubits with atomic systems. If you look at these two to one mechanical systems, they are very distinctive. As mentioned before, the coherence times typically from superconducting qubits are in the range of microseconds, whereas for atomic systems, they can be fairly long, milliseconds, or even up to seconds. Of course, the operation time, gate operation time, and so on and so forth is much longer for atomic systems, which ranges in the range of kilohertz, whereas for superconducting system, it's actually in the range of gigahertz. The question is how can we couple these two things together? We actually have come up with a potential solution. Here, the idea is to, let's say, bring atoms in close vicinity to certain components on the superconducting circuit itself. In fact, here's a schematic overview of a superconducting charge qubit, but it doesn't matter if it's charge qubit or a transform qubit. It's the same physics behind it. Where actually we place a atom, a radium atom in this case, in the vicinity of the capacitor, or the prone capacitor of the system. And then actually, depending in which state the atom is, if it's in the ground state or in a highly excited state, in a Rydberg state, it will actually influence the state or the energy of the qubit, and vice versa. So also depending actually on the state of the qubit, this will influence the let's say, Rydberg state of the atom. And let's see how this actually could, or let's say, look in reality, is actually shown here on the right, where we actually can place, let's say, on a transform qubit, which is shown on this. Just above this transform qubit, if you place there an atomic cloud, it will actually interact with the fringe fields of this electric field from the capacitors. And we have actually shown that if we, let's say, bring these two systems together, we can actually transfer the state from one quantum system, from the atomic quantum system, to the superconducting quantum system, and vice versa, with a high efficiency. So the idea is shown in, let's say, figure A, where the energy diagram of the superconducting qubit is shown, addressed with the atomic state. And then depending actually if the atomic state is in the ground state or in the Rydberg state, if it's in the ground state, we see the black line here. And if it's in Rydberg state, it's actually the dotted blue line. So if we change the, let's say, offset charge, for example, for the charge qubit, then let's say to a certain value, then only we can make a transition between the ground and excited state if the atom is in the Rydberg state. However, if the atom would be in the ground state, a transition would not be possible. And by using this effect, we can actually realize the circuit in subfigure F, where we can actually transfer a state from one system, from the, let's say, superconducting system to the atomic system, and also vice versa. On paper, this looks quite nice. However, in the experiment, it's a little bit tricky because we have to marry two different technologies together. The, let's say, atomic, hydro-cooled atom technology together with the superconducting technologies. For this, we have set up a experiment in our lab where we can actually bring atoms in, let's say, close vicinity to superconducting qubits, and also inside, let's say, cavities, superconducting 3D cavities, as is shown here. So here we have, let's say, a superconducting transquantum qubit, where we can bring, let's say, an atom very close to this superconducting transquantum qubits. And what we have seen in simulation in this case, also with a decent distance between the atom and the superconducting qubit, we get a large coupling of about 20 megahertz coupling strength, which can be actually seen as an energy shift of the cavity. So what are the next steps? The near future, of course, enhance the capabilities of our superconducting circuits towards this 10 qubits and even beyond, and explore, actually, that's more in the far future, further paths towards connecting superconducting quantum systems with other quantum systems. And I think that's all I want to share for today. Thank you for your time, and if you have any questions, maybe we still have 1 minute or so for questions. Okay. I can also answer the questions directly in the chat if necessary.
Hi, Rainer.
Yeah, hi.
Hi. Thank you very much for your presentation. I think it is clear to the audience how difficult it is to make a quantum computer. And we are just very on time, so let me ask an extremely brief question, which is, what are the most difficult piece of making the quantum computer that you see ahead? Okay, what is the technical barrier?
Well, okay, so the most difficult thing is the scaling to, let's say, I think, let's say, the most if we go beyond what we have, that's what's possible right now in the world. So let's say beyond, let's say, 60, 70 qubits or whatever, doesn't really matter. Going to, let's say, something like 1,000, then actually the whole infrastructure which I've shown has to change. So it's not anymore possible to have, let's say, all this processing of data outside of the fridge. We have to put everything, let's say, within a vicinity of the quantum processor itself. So on the 4K stage, or even on the millicable stage, and that's is extremely difficult, especially if we are going for the SFQs, RR SFQs on the millikelvin stage. They haven't, let's say, in the last. So this is technology which is fairly old, it's already a few decades. And the reason why this didn't really progress so far is because we don't have any, let's say, classical memories at this very low temperatures at the millikelvin stage. So I think that's one of the big challenges which we have to address in the midterm future.
Okay, thank you. I quite understand that. I'd love to have the 70, 80 qubits anyway. So
exactly.
Thank you.
Yes.
Thank you, Raghunath. So let's move to our next speaker. As I said in my introduction, there is a piece of news coming from Europe that a new company, IQM, has started to commercialize their products. So it's a pleasure to invite now Raghunath Koduvayur from IQM, and I hope we will learn what they have achieved.
Check. Hopefully I'm audible. Can you get the video to be played, please? All right. Good morning, good afternoon, good evening. So wherever you are and joining us today, the last 2 minutes that you saw the video would be a brief summary of quantum computers that we are discussing. So quantum computers is something which is coming out of research and is definitely a mainstream discussion. Even since the last keynote, or even in the opening keynote yesterday, quantum computers has got a mention. And this is an opportunity where I think we will build the future of computing together with all of you. In the next 10 to 15 minutes, let me walk you through IQM and also why the audience who is interested in supercomputing centers should be investing into quantum computing and should start now. This is one of the researches that we did along with Athos and IDC, so IDC Europe. HPC centers globally have said, of them 76% have said that they will be adopting quantum computing by 2023. In some form, they'll be adopting quantum computing. And if we look further, 71% of them say they will be moving towards on-premises quantum computing by 2026. And this shows that there is a hybrid model which we are entering in, like we are seeing with on-prem and also cloud. There will be a quantum computer in every supercomputing center. The third most important thing, if I was part of you and then looking at supercomputing centers, and if I was a decision maker, the challenges that I have and the priorities that I have would be these. Like, how do we get the opportunities in terms of memory-driven computing, chiplet-based computing, and quantum computing? This is globally among the top 3 technology areas by 2026. While if you look at EMEA, Europe is slightly ahead, I would say, in terms of quantum computing discussions within supercomputing centers. Their quantum computing already ranks among the top most priority area. So, here as a IQM, who are we and what's this company about? I was fortunate in the opening remarks also. Professor Torres said and mentioned about IQM, and we are glad to be here. IQM is built on the foundations from Finland's research. Finland, which has been very, very advanced in quantum computing and low temperature technologies, and has been doing a lot of research in this. IQM is a spin out of Aalto University. So we have over 4 decades of research behind us, but then we are a company who is 3 years young right now. We have already become the category leader in building quantum computers, and we deliver on-premises quantum computers. We are one of the only quantum startups in the world to have delivered an on-premises quantum computer where a customer can access the quantum computer's hardware. And this we have already installed in VTT Research Center in Finland. We also have a differentiated product portfolio, one of them which includes quantum accelerators for supercomputing centers. And we are currently working with LRZ in Germany and also CSE in Finland. And we deliver an entire full stack of quantum computers, including our own fabrication facility, design software, and also one of the largest quantum engineering teams in the world. How do we see the world and the quantum computing? So there are 4 building blocks to it. One is design, the second is foundry services, third is processors, and the fourth is OEM. So in this case, we do all the complete system. We offer everything as a system integrator. So we do the design, foundry services, processors, as well as we integrate with the OEMs. And why now? Because HPC centers right now are necessary to solve the problems of the future. So we look at climate change, we look at drug discovery, we look at finance. So there are many pain points which HPC centers are trying to address. One of them would include scaling up the computing power. And how do we stay competitive? And how do we create a strong innovation pipeline? The second one is next generation of HPC hardware is only giving incremental improvements. So there is a need to also combine a quantum hardware with a supercomputing hardware, HPC hardware. And more importantly, we should not ignore the fact on sustainability and the energy consumption challenges. This is something the climate crisis is building up on, and we have a role to play and a responsibility to take it forward. And lastly, it's not just that. Quantum computers also offers exponential computing power in the future when universal quantum computers are available. So we are getting there. Quantum computing is getting out of research to productization, as we saw even in the previous presentations, and also we will hear more, is that it's coming out of research, and now we see more and more quantum computers and also algorithms being played out, and it's important that we get started right now. So what role does IQM see in terms of HPC and a quantum computer integration? This is a brief slide in terms of the workflow, where we see that the algorithms will be coexisting both with a quantum computer and a HPC center where the algorithms will be handed over and passed back depending on the problem. So actual computation will server communicates with the HPC and a QPU server, and then control flows of information and the processes are scheduled. So this is one way we see it. The second one is the algorithms, the way it will be written will also be hybrid. So we have seen the first signs of algorithms which have the potential to deliver quantum advantage in a few years' time. The QPU circuits get executed several times, and then we also need solutions for memory access. So these are some of the things that we are looking at and evaluating how these hybrid algorithms will also be in the future. Is it still theoretical, or do we already have points to prove? So one of the things here is we are already working on it, not just delivering a quantum computer to VTT in Finland, but we won the public tender which was organized in Germany late last year, where we won the tender to build the Germany's quantum computer and integrate it with LRZ, which is the third largest supercomputing center in Germany. We will, as part of this project, integrate also with simulation software from HQS, and also hardware is being provided by Atos as a partner. And it's a 45 million euro project where we are delivering the on-premises quantum computer. And it also includes a significant amount for research and development. So this is no longer theory, but it is getting implemented. And here we are also delivering a 20-qubit quantum accelerator, which will be integrated in this HPC integration. The next one is Finland's quantum computer. I have some slides on in the appendix if you want to go into the technical side of it. But this is the first milestone that we have hit in delivering to a customer. A 5-qubit quantum computer delivered last year in November 2021. This is part of a 20.7 million euro project which we won a couple of years back, and the first milestone has been hit. The next two milestones include a 20-qubit processor and then also a 50-qubit processor. So with us, you also get an upgrade of the quantum processor. That's how we see it, that on-premises quantum computers where they can also be upgraded depending on the project scope. Finland retains with this, also becomes one of the first countries to have purchased a quantum computer, and this is part of a wider vision to establish a quantum ecosystem and maybe part of a national quantum program. This is something that also other countries can take part of or follow up on as a best practice in creating this national quantum mission. I was extremely pleased to hear about the investments that Singapore is making on these quantum missions, and these are things that I think we will see more and more in every country. And then also the second one is in terms of IQM, so we already managed to deliver this, so now we want to see how we upgrade these as part of the next milestones. The topic that comes up, sustainable future. Is it important? Like, what is the role of a quantum computer in sustainability? These are some numbers, so we are still conducting a lot of in-depth studies on the energy consumption. But if you look at the theoretical research that has mentioned, HPC clusters can use up to 10 megawatts of power, while a quantum computer holds a promise to use significantly lesser power. We will be, in the course of this year, doing some more research on the energy consumption and also sharing data, exact data around that. And also the second one is advanced scaling of energy. So this becomes HPC is quite linear. So depending on how many tasks you have, how many processors, the energy consumption increases. But quantum computing will likely increase modestly because the upgrade with the same cryostat will not be significantly higher or not linear. So there's another reason why we should move towards a hybrid computing future. And also, we will have reduction of energy consumption. So for me, in this session, before I conclude, there are two things which I want to definitely highlight. The first one, for everyone who's participating in this call and following the live stream, we do want to collaborate with you. We can collaborate at multiple levels, right from software, chip design, research, or look at partnerships with supercomputing centers where we can build quantum computers for you. Together with IQM, you are not just participating with one organization, but we are participating with the entire European ecosystem. We believe in that way of working where research can only accelerate through a joint partnership and collaboration, and we role model that. We have 4 offices, so where we are already actively working on, and we have a significantly large quantum algorithms team in Munich, while the hardware team right now is in Finland. And then the next one, which I would also want to, if you're interested in this topic on superconducting qubits, is the SQA conference, which is being organized as a not-for-profit scientific conference to accelerate discussions around this topic, both in terms of HPC integration, but also in terms of the quantum computing and quantum technologies in general, more focused on superconducting qubits. So if you are in this role or in this space where you're following this space, or if you're interested in the way the future of HPC integration would work with supercomputing centers, then please do register for this event, and then it sounds to be promising. With that, I'll be open to take a few questions. Thank you.
Thank you very much. It's very impressive, may I say.
Thank you.
And congratulations. Yeah, let me ask you a question. It is clear that the Centers for Supercomputing are joining the race, let me say, and they will host quantum computers. What is your opinion about large corporations, in particular in Europe?
A very good question. I have some data, so I'll relate to some data that has been done as a research, which has already been publicly published. But then the initial discussions, I'll also share that. Significantly high number, close to similar, 70 to 75% of industries plan to use or are considering quantum computing in some form or the other. So corporates are getting started in Europe in investing into quantum computing. But where they are in very early stage. So they are not using quantum hardware. So they're just testing out some algorithms and maybe a quantum cloud. Where we see the future evolving is most of these large organizations also have, let's say, any large automobile player or other pharma business, they own their own supercomputing centers or they partner with certain supercomputing centers. There we see interest to purchase a quantum computer. Not yet, but soon it's coming up. At least the discussions seem promising. While if I take the Finland's example, where corporates are not that big yet and they don't have such deep pockets with R&D. So they are working with the government and the National Research Center to establish a national quantum program where VTT has purchased a quantum computer and they will enable the local corporate ecosystem to start using quantum computers. So they'll start practicing, if I can call it, piloting quantum algorithms there before they make their capital investment into purchasing quantum computers.
Yeah, I agree. So we will see the development of hardware as something that we don't understand well yet, but also the market. No? The market is very unclear how it will develop. It will develop enormously, but we don't know how.
Thank you.
So thank you very much and congratulations.
Thank you very much. And then have a great rest of the session. So thank you.
So in the first talk, we had Rainer telling us how to make a quantum computer. Now we have listened to AQM and about their plans and how to expand very fast. But we would like to go back and understand better how the quantum computer works at the level which is not hardware, but the full stack that controls it. For these, there are many options nowadays. Some are proprietary, some belong to corporations. And there is an open source initiative called Qibo, and Stefano Carrazza is leading this initiative, and we would very much listen how a quantum computer will be controlled, okay, in an open source framework. Please, Stefano, by the way, is talking from Milano, and he has a very extensive experience in programming everything, artificial intelligence to quantum computers.
Thank you, José Ignacio, for the presentation, and thank everybody to join my talk. So today I would like to present Qibo, which is our open source project. As you can see from my and hybrid quantum operating system. So let me start from an introduction, which is attached to what we just said from what we have just listened from Rainer and the previous talk, IQM. We are in these last years, we have been seeing a lot of interest in quantum technologies, So many fields and many, let's say, applications are under development. And one big issue when talking about research and development of novel quantum technologies is how to control, how to simulate and design algorithms. If you check out what happens today, you see that many companies or many research laboratories, they are developing in-house software, and this in-house software is in many cases closed source, at least for the control units. Now, you can also find frameworks for simulation, but in general, when going inside the laboratory, you find the closed source developed. And together with that, there are a lot of code and effort duplication. Now, many people and many groups are reproducing again and again the same routines, the same algorithms for calibration, for characterization, and this is really a lot of effort that could be optimized, or at least standardized. So in this context, we can state that there is no full open source framework that includes all the specifications to operate a quantum computer. There are many pieces, but these pieces, as you can see in this cloud of words, from the language API to the remote access to the cluster infrastructure and to the hardware control, a complete framework with all these components is not available yet. Now, just let me take and explain a little bit what are the degrees of freedom when dealing with a quantum computer. From Rainer's talk, we saw this process. On the left side, you have the transmon, the qubit. This object is located inside an experiment. This experiment contains several instruments and devices. And usually when talking about superconducting qubits, we have to bring this system to very low temperatures. So we need a fridge. We need to control the fridge and make sure that the full pipeline is up and running. The center plot where I'm showing the experiment design, it contains laboratory devices. Distributed into hardware and eventually products. And the idea, the final idea, is to have a pipeline which injects pulses and another pipeline which read out the information. So we can prepare the state, prepare the system, and then perform the measurement. To make this system and this procedure happen, we have to set up different experimental devices, from microwave sources, from local oscillators, and amplifiers and FPGAs. And in many cases, all these objects will be connected into a network, the laboratory network. So this is the way we have to communicate through the different experimental devices. So the big first question is, how can we control quantum process units automatically, given a system where there are an heterogeneous number of devices and all of them are connected into a lab network? The second question raises from the plot that Rainer showed before, the Icarus cube. As soon as you start growing and increasing the number of qubits, the system complexity increases. So you have more devices, you have to synchronize all of them, you have to perform scheduling operations, asynchronous scheduling operations for pulse input and then readout reconstruction. And finally, we have to calibrate the full procedure and the full platform. So this brings us to another question, is how to synchronize and calibrate the quantum process unit platform. And the final question is, given a system composed by multi-quantum computers, or say a laboratory with different experiments and platforms connected to a network, how can we connect the quantum process unit setup to a HPC cluster and then bring access to the external world through a remote connection? So this is ideally the best we could do today. So bring together the quantum computing technologies with HPC technology. So we can at least try to, from one side, have a software for scheduling, preparation, and submission of quantum process unit jobs, but on the other hand, have the support from HPC in order to perform high-performance hybrid quantum classical algorithms. Now, if you wanted to make a quantum machine learning, for example, or any other application that requires a not negligible amount of classical resources. So, if I summarize the previous points, you see that all these questions that I have raised before, they require a solution, and Qibo and the Qibo project tries to address all these problems. So from a user perspective, we start from the problem, we code the solution, and then we delegate to the project the possibility to execute, or from a quantum perspective. So in both cases, we have the automatic mechanism to switch from one to another. So now I can move on and just tell you some points concerning Qibo. So Qibo provides an ecosystem with a language API, with quantum algorithms and models, and most importantly, examples, tutorials, and laboratory tools. So it's a project oriented to research from one side, but also with a huge focus on laboratory, on research laboratories, and the possibility to accelerate research on that field. So help experimentalists to develop new technologies, try new technologies, and do not spend their time developing or reinventing the wheel, reinventing again and again calibration procedures and different practical algorithms that are needed in the lab. The project was born in a international collaboration between Asia, Middle East, Europe. So we have different countries and different technologies involved from Spain, from Singapore, and for example, in Abu Dhabi. And Qibo provides a language API which supports two different paradigms: quantum circuits from one side. So we provide primitives for circuit allocation, gate definition, measurements, and optimization, together with pre-coded models, variational models for example, VQEs, machine learning applications. And on the other side, we have the possibility to use quantum annealing techniques such as adiabatic evolution, scheduling optimization, time evolution, thanks to a large database of Hamiltonians and different algorithms concerning interiorization and so on and so forth. Now, yeah, unfortunately, my slides are not working so well today, but I can tell you that in Qibo, we have implemented several backends, simulation backends, and hardware control backends. They are using different technologies, so they can be adjusted to CPUs, to GPUs, or to multi GPUs for the classical simulation, and automatically can also be deployed on quantum hardware. Here you have an example of simulation. So on the left plot, I'm showing the total simulation time for a growing number of qubits. So in the x-axis, you see the number of qubits from 3 qubits to 36 qubits. And the curves that you see here are the total simulation time performed with Qibo using a high-performance state vector simulation library module that we have developed. So as you can see in this case, we can go very far in terms of qubits. We can go up to 36 qubits if we provide a machine with CPU and a lot of memory, 2 terabytes. So that's important. We can scale linearly with memory. We could also try other configurations. For example, some colleagues at CERN that have access to the Atos machine, they have tried Qibo there, and thanks to the 6 terabytes available in the Atos QLM, they can reach 38 qubits. And so Qibo can also work on heterogeneous hardware, even if commercial solutions such as Atos. If you compare the CPU performance to the GPU, This is also done automatically by Qibo, and you can also get a lot of improvements in speed. Obviously, you'll be bounded by memory, so you cannot do much more than 31, 32 qubits. But as soon as you understand that your problem may have some benefit from GPU access, plug multi-GPU and use the Qibo multi-GPU implementation that you see here on the bottom plot. So multi-GPU improves the performance and can give you some advantage in the computation. In terms of syntax, the code is very simple. As you can see here on this screenshot on the right side, create a circuit, allocate a circuit, and execute. It's pretty simple. It's very similar to other libraries. So the level of difficulty to integrate your current framework or your current code into Qibo is very low. So the barrier is very low. In comparison to other libraries, Qibo is quite competitive in terms of simulation. So here you have 2 examples of simulations, the total write time, so the simulation time for a 30 qubit system in single precision is the first plot. And in the second line, you have 30 qubits in double precision for different circuits: the quantum Fourier transform, the variational circuit, the supremacy circuit, the quantum volume circuit, and the Bernstein-Vasarany circuit. And we are comparing Qibo, which is the dark blue for GPU and the light blue for CPU, against other libraries like Qiskit, QSIM, HybridQ, QCGPU, Culex, and Project Q. And as you can see in all these test cases, our performance is good, it's compatible with other libraries, and in some cases can also be even more efficient depending on how you define the problem. So that's to show you the level of quality, level of efficiency that we have. Now move on to QPU control, so quantum process unit control. What we have included so far is the possibility to have a generic transpiler inside the code, which can take advantage of multiple instruments. So Qibo can convert the circuit, so you just write, the user writes his favorite circuit for his specific target platform, and then Qibo will automatically translate the syntax into wave function generator pulses, local oscillator operations to modulate the signal, and amplifiers, and eventually other devices like the Q-Blocks devices and custom FPGA boards with radio frequency sockets. So we provide a large database of instruments that can be automatically deployed and can be integrated through this transpiler. The interesting idea about the project is the possibility to support multi-platforms through run cards. So if you have a new configuration in your lab and you'd like to test it, it's quite easy. You have just to introduce the instrument definition in the code, set up a run card with the different configuration parameters, and then Qibo will apply the transpiler out of the box. And this is very interesting because then from a practical perspective, for example, here I'm showing a very short example where I take a single qubit in a real machine, in this case, the Abu Dhabi system, the QRC TII system. I allocate a single qubit and then I apply rotation over X for a specific angle. And then I can try to rotate and measure the system several times. So you see in few lines of code, I have already an experiment which is measuring 1024 shots every time I change the angle parameter of my circuit. If I do that, you get a plot like the one on the right side. The solid dark curve is the simulation output, which can be obtained with Qibo by varying the angle value for the rotation. While in the purple, you have the experiment output performed directly into the quantum PU hardware. So you see that they are matching the two curves. So this process is performed automatically and is executed when you launch the circuit measurement procedure, where the circuit in Qibo is translated and transpiled into pulses and pulse sequence, and then this information is sent to instruments and drivers. And all of these operations are controlled through threading. What we have so far with the quantum computers. Finally, for concluding the QPU control, the library provides calibration and characterization routines. For example, the resonator spectroscopy, Rabi, and Ramsey interferometry procedures to determine the different parameters that are needed in order to calibrate the system. And all these tasks are designed to be completely generic. So if you change platform, the procedure will be the same. You can eventually customize if you need, but everything will be automatically done, and will also be scheduled into periodic systematic job that can be run several times during a day, during a week. Yeah, so with that, I arrived to my conclusion. So in summary, Qibo is a framework which has already 1.5 years of development and has a good simulator. It's a good quantum process unit control, which is being developed in collaborations with other labs. It's designed with a modular and open source approach. It's community driven, so this is important. Many people are involved from different places, and we are trying to bring this software in such a way that everybody in research can get an acceleration, can achieve success as soon as possible, reducing the amount of code duplication. So if you are interested, I would just invite you to look at the repository, to the documentation, and if you have any questions, just just write to us, and we'll be happy to discuss. Thank you very much.
Thank you, Stefano. So this is a sort of Linux for quantum computers. Let me ask you, what are the plans to include other platforms which are not superconducting qubits?
Mm-hmm. Yeah. So currently we have superconducting technologies in 3 different labs, and we will start the implementation of a ion trapped system in the CQT in Singapore. And the idea is that we don't have to modify the code or the base Qibo module that operates a quantum process unit, but we will have to incorporate new instruments that are used on that specific setup. So at the end of the day, the Qibo lab module will include several run cards that explain to the code how to operate and how to translate pulses into the appropriate instrument. Eventually, if you need some other representation, we can have another representation. The transpiled is flexible enough to support and integrate different definitions.
So thank you very much, Stefano, and good luck with all the project. So let me now invite the people to the panel. So it's José and Tommaso. Let's go over there. Hello, good afternoon, and thanks very much for coming. So it's a pleasure today to have this panel discussion. Let me motivate it. So in the beginning, we had Rainer making a quantum computer, IQM, also making quantum computers, and we have listened to the middleware that controls the detailed actions on the qubits. So we are missing how do we use these quantum computers, and what are the challenges of using the software challenges to use a quantum computer. And for that, we have a panel session with 3 startups that are progressing very well. It is, in this case, Horizon. We also have Entropica Labs, and we have AngelQ, which is online, I think. Hi, I see now Dimitris. So this is the purpose of this panel, is to be as open, in my opinion, as possible with the community so that they understand the real issues. Because there is a lot of hype, a lot of misunderstanding, a lot of naivete. So I think that, in my opinion, it was essential to have people that work, there in detail and can bring their opinion in a very open way. Is it a little messy not to hear and to talk all the time? But anyway, so given that I have José from Horizon, Fitzsimons, he was a former member of CQT, and now he's having this very successful startup. I would like to invite José to tell us a little bit about his vision, about what your company is doing, and in general about the software developments for quantum computation.
Sure, so thanks very much, and thanks for inviting me to be part of this panel. I should start off by saying that I agree with what you said about a lot of hype going around at the moment. But I think one of the things about quantum computing is that it's both simultaneously overhyped and underhyped at the same time. So prospects for big advantage in the near term are definitely overhyped. And I think a lot of people don't anticipate the difficult path ahead, the level of technical innovation that is still necessary to get us to a place where these machines are actually providing an advantage to industry. On the other hand, if you take a long-term view of quantum computing, it is ultimately something more than just a coprocessor. These are not ultimately devices just for solving optimization problems. They are general computers, and they're better computers than the computers we have now. And that has the potential to open up tremendous value if we can figure out how to build the devices and how to take advantage of them. Now, that's kind of where we come in. I guess you've heard already about building the devices. We don't try to build devices at all. Where we come in is in terms of how to take advantage of them. So we're concerned about how does a user take advantage of quantum hardware in order to solve a problem that they might care about. So that problem could be something, okay, you see it a lot of the time with optimization problems and things like that people focus in on now, but there's a huge range of problems out there that are using high performance computing all the time that don't fit into the model of the existing algorithms. So things like computational fluid dynamics for turbulent fluid flow, the kind of inverse problems you have in oil and gas, the kinds of problems you have even with simulating lithography for semiconductors, different things like this. And actually a lot of these problems are the kind of thing that should get a good quantum advantage. They have the right structure to get a good acceleration. But the fact is, none of us in the industry, none of us in the quantum computing side are expert enough in those areas to be the one developing those applications. And the people who have the domain-specific expertise for those applications, they're not experts in quantum computing. So it's unlikely they're going to come up with something that's like Shor's algorithm, a huge breakthrough. So where we come in is trying to enable that. And the way we're doing that is to build a system that takes in classical code, code written in MATLAB or Python or Julia, something like that, and being able to automatically construct a quantum algorithm that does the same thing, but more efficiently, and then compile that all the way down to the either gate level or pulse level operations, to the kind of level of Qibo that we've just heard about. So we're going all the way down, synthesizing between different instruction sets, not just for particular systems, but between general sets of Krauss operators or POVM elements. So we can really handle systems of arbitrary dimension, arbitrary different kinds of gate operations, arbitrary physics. So that's what we've been doing, and really with that we're trying to build a bridge between the end user and the systems. But of course, for this to be useful, the hardware needs to come along too.
Thanks, José. Let me use one of your introductory ideas that I like a lot, that there is another hype and another hype. I completely agree with that. So it is perfectly compatible to understand that the power of quantum computation is enormous with being cautious in the short term. Okay, that is like something which is always a trade-off. I have a question later, but maybe we go first through a round of opinions. Okay, so Tommaso, Entropica Labs, could you tell us a little bit what's the purpose of your company and how have you been working this recent time?
Yeah, absolutely. I also thank you for the invitation, and I would like to thank Joe for the introduction. I will say that I agree with the thought of overhyping and underhyping quantum computing. And we are taking a different approach that Horizon is taking. We are thinking about it much more bottoms up, if I can say. Let me also remove this. So the idea is the following. Since that now we have quantum computers available, something that we as a company really want to understand very well how to do is how to use these machines and get a good sense of all the bits and pieces that are missing at the, let me say, software layer or software architecture. So earlier, Stefano with Qibo gave already a very good introduction. And what we are doing right now is to focusing on a specific area of application, which is applied mathematics. And even more specifically at this point of time is to look at optimization problems. So Joe mentioned optimization a few times. I fully agree with him. Quantum computers are not going to be devices that are only going to be used for optimization, but they are universal computing devices. But what we really want to do at this point as a company is to understand how we can take certain problems and solve them using the quantum computers that are available today, making sure that the software scales up as the machines grow in size as well. So what we are doing, I guess it's fair, there is threefold. On one end, we really like a lot to think in terms of classical computers. So classical computers are incredibly powerful, as we have been hearing a lot during this event, and as we will hear more. So a big part of our work is also based on this idea of benchmarking quantum computer. So to make sure that we have good metrics to make very meaningful statements about whether quantum computers can solve problems better than classical computers in this near-term era of the technology. Also to avoid the kind of hype that we were hinting at. So that when we make statements, these statements are actually solid and are ideally quantifiable. So we are building a whole suite to perform benchmarking of optimization problems using classical algorithms. And at the same time, we are also thinking a lot in terms of how can we easily deploy quantum algorithms on near-term devices in order to solve the problems of reproducibility and making it easy as possible for developers to use the machines. So we're also building Python libraries that allow, well, first of all, us and eventually other people as well, to run certain quantum algorithms as seamlessly as possible across a number of available devices. And the last point that I would like to emphasize, because I think is very important given the moment we're in, is that we're still performing somehow more fundamental research in quantum computing, looking at different ways to design algorithms, given the resources that we have available today.
Thank you, Tommaso. And again, I have a few questions, but maybe we go for first round and then we open the discussion. So Dimitris, you are from Crete, if I'm correct.
Yes.
And we would like to know what AngelQ is willing to do in quantum software.
Right. So yes, Crete is from Crete. I am in Crete, but AngelQ is based in Singapore. I'm traveling Europe at the moment. So I we also kind of belong to the software space, quantum software, quantum algorithms, but we closely also kind of look at what can be done with the current hardware. So that's because just the background of myself through the academic side, the last 2 decades is really trying to squeeze as much as you can out of the current hardware. So I kind of aligned with both Joe and Tommaso earlier on the usefulness and the under-hype of quantum computing. I think, yes, quantum computing is hyped in certain sense, but it's also under-hyped. There's a lot of areas we could develop more. Specifically, what we try to do at the moment is to focus on 3 verticals. Quantum-enhanced data analytics. You can also see it as quantum machine learning in a sense, but for real-world problems and data from specific areas, especially market research. The other one is optimization, especially energy management, grid management. This is something we found very exciting and something that near-term and current quantum devices can squeeze some value out. Just seeing the energy crisis happening in Europe these days and all the mess on the East. Further down the line, we would like to probably go a little bit more into quantum finance, but that's something we're not doing at the moment. We want to focus on what I mentioned earlier, quantum data analytics and optimization for supply chain and energy. We work both with fully quantum in the context we had earlier, but also a lot of quantum-inspired algorithms. This can be either hybrid quantum classical, but also fully classical algorithms with that have some quantum angle in it that can help deliver better solutions in these 3 verticals. What I see personally on the balance between hype and anti-hype, I think we really need something soon on the real kind of business value in any of the areas. It doesn't have to be everywhere. So that will keep the momentum going. I can see it happening soon. The hardware is evolving very fast. 20 years ago, when maybe I'm the oldest in the audience, except after JI. Sorry, JI. There's 20 years ago, my PhD was in 3 qubits, 4 qubits. The last 3 years, we have, almost doubling the number of qubits every 2-3 years, which means very soon we'll be able to deliver, hopefully, devices that can, with the right algorithms, can deliver some real value. And I think this is what is really needed at the moment.
Thank you, Dimitris. So let me now to a second round of questions. And the first for Joy. You see, I want to put myself in the skin of the people that are in the market, in the economy, not in the scientist point of view. So to what extent developing a good solution for a real company depends on understanding the detail of the hardware. So are we at the phase that the knowledge needed in your company is really a deep knowledge that related to the hardware? Or are we at the level of libraries that solve things in a more simple way, let me say?
So for us, this is a little bit different. The way we're structured as a company, the way we look at creating value is in terms of technological progress. So we need to advance the technology to the point where it's actually useful, because the current devices are not at the point where they will deliver an advantage to businesses that will affect their bottom line at this, today. And we don't know exactly when that line will be crossed. And you're right, in order to take advantage of hardware, you need to put a lot of effort into optimizing an algorithm for the hardware. For us, we do this programmatically. We don't do it with manual intervention. So we try to automate all of what a human would do. We do that at the level of algorithm construction, in terms of how we structure the algorithms, but we also do it as we go down as we start to translate the basic structures of an algorithm into a concrete circuit, mapping it to hardware, and then optimizing for that hardware. And that means doing kind of people optimization, where you're looking at regions of the circuit, seeing if there are mathematical transforms you could do or replacements you could do that would get you to something more efficient. And you need to put a lot of effort in there. But that's not enough. You need to go deeper down. And that's because the hardware today, as you know, it's just not at the point of being highly reliable. You can't rely on it to give you the correct result every time. The reality is all of your qubit rotations are a little bit off, there's a little bit of dephasing, there's spurious two-body interactions that aren't mapped out in the processor. There's all sorts of little things conspiring to give you the wrong answer. So if you try to make too long a calculation, it will give you the wrong result. So for us, we need to mitigate that. So we've put a bunch of effort the whole way down the stack, going from a very abstract level to a very, to the level of pulses, to the level of frequency calibrations, and to the level of things like decoupling sequences. Basically so that we've built up algorithms for more efficiently characterizing hardware, working out the two-body interactions within a particular processor, and then trying to mitigate those through a combination of retuning qubits, for example, but also actively intervening during computation, structuring the computation in such a way that we take advantage of symmetry in the noise to cancel it out. Now, of course, that's not perfect. We just need to do what we're trying to do is do the best we can to get the best performance out of the hardware that we possibly can for whatever hardware we're faced with.
So, let me be extreme. Do you see yourself in any future co-designing the architecture of the chip?
So actually that's something we've been interested in from the start. If you look at the way quantum computing needs to go long term to get to a region where there's real advantage, you run into problems like what will memory architectures look like? How do we store and retrieve quantum information? What do different regions of a chip look like? At the moment, they're, largely homogeneous. Maybe there's edge effects or something, but it's often a regular pattern tiled out or something like this, or some particular graph. But if you look at the way a processor is structured, you have an arithmetic logic unit, floating point logic unit, and so on, and those are wired differently. They're different circuitry. And different connectivity on a device would certainly lead to higher performance with specialized regions if we get to the point where there's low enough noise in the qubits to take advantage of it. And even for implementing logical qubits, that kind of design is important.
Yeah. Okay, Tommaso, I would like to raise another issue, which is that many people...
Can we stay on this one moment, J.I.? Just a quick intersection on this. I think the good design idea, at least for us, is very, very important. If we think of the stack, lower down here, there's a quantum device. The quantum device, there are electrons or superconductors or something very quantum and quantum physicsy. At that level, everything is described by what we call in physics Hamiltonians and analog approaches. And then higher up, you have the digital version and the composition so on. Personally, I find it very exciting to look, and we're doing some research on that direction, on the analog quantum computing approach, whether one could actually even get away from the digital and the quantum gates completely and design, compress the kind of lower level of the stack into and extract the optimal analog juice that is hidden there. So we found some signs that this works, even for machine learning, quantum machine learning. You can train models, you can do generative modeling, you can learn distribution, just using what is there by nature. Whether that will deliver results to any other areas of quantum algorithms, because by default we write quantum algorithms using the digital approach. That's how we learn to do it. I don't know, but I find it very exciting, and it goes in this co-design direction.
Yeah, I think in the short term, this is a relevant issue. In the very, very long term, I don't know. So, Tommaso, I wanted to raise a question of how difficult it is to acquire talent Okay, there is a shortage of talent, and how we have to deal with that. But in particular, you know, in case we are listened by people from other fields, what are the opportunities that you see for engineers or for other mathematicians, whatever?
Yeah, there's a good question. Acquiring talent is certainly a complex issue at the moment, because I believe, as many of the people who have been here at the conference have witnessed or have experienced, a lot of people are talking about quantum computing. It's becoming more and more of a hot topic for good and bad reasons, which means that there is a lot of excitement, there are a lot of expectations, and especially we have big corporations like the largest cloud providers on the planet who are investing heavily into this technology, which means that they need people, and they usually have financial means to hire people in ways that startups, you know, may struggle with. So this is just to set the context a little bit. When it comes for a company like Entropica, when it comes down to us, it is certainly a struggle, but I can also say that we have had good fortunes because, you know, I come from CQT. I mean, everyone here in this panel actually comes from the Center for Quantum Technologies, and some of the people who are working with us today were either PhD students at the center, or they either studied or performed research during their undergrads or master studies with one of the PIs at the center, which is fantastic because then they can reach out to us and they've already acquired knowledge or expertise, and they're also really intrigued. They're in the right mindset to start a career in quantum computing. And I'm seeing more and more of very talented students who desire to spend 2, 3, even more years with a company, with a startup, before they go and do a PhD. In my experience, this is quite new. When I did my PhD, this was not the case. Most people would go straight from, like, you know, undergrad, master into an academic career, if you like. While now we're seeing more and more younger folks who have a strong desire in actually getting their hands dirty and really learning the more practical details of the technology before considering whether they want to start a PhD or not. Another important channel for us has been working closely with universities. So there are, especially in Europe, you have a number of really excellent universities who offer, well, they have their own internal internship programs, and they're usually quite open when it comes to collaborating with startups. Even if we are, in a way, we are on the other side of the planet, they're very open and they're very supportive when it comes to connecting students with a company like Entropica. And what is also very positive is that some people come, they spend 6 months with us, and then they stay for a full-time position. So yes, it is a big challenge, but I have to say I'm positive because I see more and more initiatives across the whole spectrum to bring talent to interact more with startups and with the industry.
Thank you, Tommaso. It was done in purpose that the 3 startups are from CQT, because it is often not mentioned how relevant is to have a strong research centers in a country. As a matter of fact, the only startups that there are here are coming from these centers. And this is the message. You have to invest in basic science to, in the future, have applied science. We are coming to our last 5 minutes. So let me ask you, starting with Dimitris, a final round of ideas. Either you choose, or I suggest something, which is, you know, we are probably listened by people who don't know really a lot about quantum mechanics. So could we go down to something specific they can understand on that you are trying to do in your company? Some problem that you are solving, something that is tangible, that is understandable, not high-level discussion. Okay. Dimitris, you have worked a lot on applications, so maybe you can start with some example of things you can do. 5 minutes total, huh? 5 minutes total.
Yep. Thank you, Jay. Yes, as I said earlier, we're looking at 3 verticals in optimization, supply chain. So one problem that we've been trying to solve with quantum mechanics is this mind-boggling explosion of possibilities when you do route optimization problems. This is very broad. This is applies to shipping lane optimization, to how we ship our oil and gas, very relevant these days, all the way to how we do our energy management systems and grid optimization. Quantum mechanics promises to solve this very efficiently, and we see some signs on that. And also we try to see how to bridge. Is very important, as you said earlier, the co-design approach. What the hardware can do at the moment, the software, I think, should really look very closely on that. And that's something we are trying to develop through this analog approach, this kind of natural quantum mechanical language, which is very different than the digital language of information in certain sense. We have to map one to the other. So we're trying to see whether you can really do computing based on this natural Schrödinger equation, as we say, quantum physics. We see some sign that this works. I'll stop here. I don't want to take the time. Just want to mention one thing on the previous thing. I also believe talent development is extremely important. Competition is huge. We have to train people by any means, and we need support on that in any way we can to do that in a large scale, because I don't think money will be a problem in the next 3 to 5 years, but finding people that can do good stuff, understanding the details is not that trivial, either for private or for public endeavors.
Thank you. May I ask you, Joe, about something tangible?
Sure. So for us, we aim to make your code faster. That's basically what we're all about, taking general purpose code that's written to solve hard computational problems by experts in that domain and making it run faster on quantum hardware. That's the goal we're going for.
Something like solving linear equations.
Turbulent fluid flow, for example.
Okay. So that if people want to address to your company, they know.
Sure.
You understand?
Yeah.
Tommaso?
Sure, I'll answer it slightly differently. So the biggest objective that as a company we have for this year is to run a quantum optimization algorithm on 100 qubits. 100 qubits, of course, is the number we have in mind. It's not so much about the number. What I mean is to run a quantum computation on a device that is considerably larger than what is available today. Now, there are a lot of problems there that are not intrinsically quantum, but they are related to quantum computing. So I'll give you one. This is a problem of qubit routing. It's related to what Joe was also mentioning earlier. If you draw on a piece of paper a quantum algorithm, that's nice. But once you have to take that schematics and actually map it to the topology, so to the real topology of a quantum circuit, of a quantum computer, usually it's not so easy to do that. And what happens is that there is a huge overhead in the number of gates that you need to actually implement that specific algorithm. So something we've been working on a lot, quite successfully, I have to say, is to come up with, in this case, classical techniques, classical optimization techniques that minimize the number of gates that you need on that given topology to actually run a specific optimization algorithm, which is called QOA, Quantum Approximate Optimization Algorithm.
Okay, thank you very much. I think we are right on time. Any comment by any of you?
Well, I will say that the point you raised earlier is incredibly important and very relevant for us. Without investments in research, especially for a country like Singapore, it will be hard to compete with, bigger countries and bigger entities out there. So we are very lucky because we are here talking about quantum computing, and CQT has certainly been what has driven all of that. So my comment is to continue doing so.
Okay, next time we will bring here venture capital, okay? I think this is what we are really missing. I don't know why we are having this thing that we all agree on everything. Okay, so let me thank Dimitris, Angelakis, and AngelQ, Tommaso, and Entropic Labs, Enjoy, and Horizon. Thank you very much.
Thank you.
And now we move to the very last. Oh, sorry. Let me.
Thank you.
And let us move to the very last talk. Now we have Pep Marturey, and this is a completely different vision of the field. So now we are talking about having quantum computers in supercomputer centers. And we are asking the vision from somebody who is running a supercomputing center. Pep?
Hi, good morning, good afternoon, José Ignacio. I hope you all hear me well. Right, let me, if I'm able to administrate my slides. Okay. Okay, I see that I can control my slides. So, well, thank you very much again for the invitation. It's really a pity not being there presentially, but let's see if the next year we can attend presentially to the Supercomputing Asia. As Professor Latorre has said, my main aim today is to give you a general outlook about, I would say, the European quantum computing strategy from the point of view of a supercomputing center. This is the outline of my talk. I will try to be very precise with the time because I've seen you've perfectly stick to the time you have devoted for this. So I'm not going to any technical detail. As Professor Latorre has said, my main objective is sharing this European strategy. I will explain also some major initiative on quantum computing related to HPC centers, but not just explaining what they're doing in Germany, in France, etc. But I will try to communicate what's behind all these initiatives, which is the global strategy for Europe in terms of linking quantum computing with HPC. So as you can see here, I will begin a little bit talking about politics, European sovereignty, and things like this. Then I will give you a brief view around the major initiative in technological sovereignty and scientific, the biggest scientific initiative in Europe. I will focus on HPC and quantum, underlining the link among two disciplines, and then going through some national, regional initiative, and finishing with some conclusion. So let me begin by the very beginning. Let's see if it works. Okay, perfect. So if you take a look to the main trends in terms of European policy related to science, technology, etc., probably you can find in the last few years a lot of statements around what's called the European technological sovereignty. It's not a matter of, like becoming a new European nationalist or something like this, because I think I don't have to explain that Europe has, let's say, a strong tradition as an open market, an open society. But it's just a matter of not relying only on foreign technology. It's a matter, in fact, of industrial and economic competitiveness. And I think the pandemic probably has shown to us how dependent is Europe to foreign markets in many things, from masks to vaccines, many technological manufacturing, etc. And I think this has driven this idea of how crucial it is for Europe to invest in its own technology. So this is something that is affecting many fields. Later on, I will show you some examples, but I will focus on what's happening in HPC, in supercomputing, and also in quantum computing, because I think it's very paradigmatic of what's going on here. What triggered this new idea, this new trend of European technological sovereignty? Well, there have been a lot of things. We can talk about the pandemic, even before we can refer to many geopolitical events. But probably the best example is a political summit between China and the States that took place on the first semester in 2015. I've just here reproduced for you some of the newspaper highlights after that summit. You can perfectly see the main words here. So war, fears, block, race, ban, etc. And this type of political outcomes probably push European leaders to develop, let's say, a different approach, a more European-based approach for technological and scientific policy. This led to Jean-Claude Juncker, who is the former president of European Commission, on the second semester in 2015, to talk about which should be the vision for Europe becoming in the top 3 world leaders in HPC. And after a few years, I like to highlight the last statement of Ursula von der Leyen, the current president of the European Commission, announcing what's called the new European Chip Act, which, being honest, it's not still very clear what we're talking about, but what it's clear is that this is on the highest political table, in the highest political agenda, and it's becoming something really central for our politicians. So there are some major initiatives around this idea of technological sovereignty. We can talk about Euro HPC in terms of supercomputing. I will talk about this now. We can talk about the quantum flagship, also about other big projects around microelectronics, electric batteries, hydrogen energy, etc. All around this idea of becoming again as much autonomous as we can as Europeans, but probably let's see, the biggest, the most ambitious European program recently launched is what we call the Recovery and Resilience Facility, or also known as the Next Generation European Union Funds. It's an enormous program. You can see here more than 800 billion euros for the next years, trying to boost the European economy after the pandemic. And this is very relevant because, as you can see here, if you take a look to these words highlighted here, some of the topics for this European large investment are very related to HPC, to digitization, to the cloud, to processor, to microelectronics, etc., etc., etc. So if everything goes as it's planned, I would say that some of the major initiatives in technology, in computing, in quantum technologies will have remarkable budgets in Europe to make progress for the next years. As I've said before, one of the main initiatives is the quantum flagship. Probably most of you know very well this program. Is a pretty ambitious program for the next 10 years. It began in 2018, if I remember properly, and is now beginning to give the first results. But let me just focus on HPC, on supercomputers, and talk about what's going on in Europe around the HPC policy. 2 years ago, the European Commission and all the European countries participating in the European Union agreed on creating what's called a new joint undertaking, Euro HPC, with two main objectives. On one side, the first objective is to guarantee to our scientists the access to the best possible HPC machines. So it means buying all the countries together, the best machines in Europe. I will come back to this a bit later. And the second objective is, on the mid-large term, putting inside these machines as much European technology as it's possible. So developing our own processors, microelectronics, etc. Around this framework, it's an important white paper that I think it's been referred by Professor Latorre before. He's one of the authors. This paper refers to how to push for a quantum computing and simulation infrastructure around the HPC framework in Europe. This paper is being supported by the most relevant people in HPC and quantum computing in Europe. And I have to tell that it has been anonymously accepted by the countries and by the European Commission, because it's pretty clear today that the convergence of quantum computing around the HPC facilities is something that it's going to happen, and it's already happened. To illustrate this, I will use these two slides of Professor Antivasara, a good colleague. I think it's something that I'd like to highlight again, although probably it's pretty obvious for some of you. We will need different type of algorithms. We will need to facilitate the development of these hybrid classical quantum algorithms with platforms including HPC machines and quantum computing machines. So everything gives us the clear idea that probably the best place for the future quantum computers, at least according to European strategy, is without no doubt the places where the biggest HPC systems will be hosted. Well, let's talk about this, because at the end, these are very relevant ideas. These are nice things to explain, but where's the reality? It's really happening something concrete, something precise that we can talk about, the new quantum systems. Well, at least what the European Commission with all the European countries have agreed recently is a map for the next biggest machines ever seen in Europe in terms of supercomputers. You have here the already approved plan, which includes 3 big pre-exascale machines around 200 petaflops, Olympic, These machines will be fully operative at the end of this 2022, more or less. Also, 5 smaller petascale machines in other smaller countries. There are also 2 big exascale machines planned in 23 and 24, likely hosted by the national HPC centers in France and Germany. But what I'd like to underline here is how important it is for Europe to have a very well planned for the HPC systems during at least the next half a decade in our continent. Around this set of HPC machines, it's pretty easy for us to open new programs like the one you have here. This is a screenshot from the Euro HPC World Program for this 2022. And it establishes what I've been saying before. Let's go for acquisition and operation of new quantum computers, and these computers or these simulators has to be hosted in Euro HPC supercomputing centers, in national HPC centers, just in order to provide to the users these hybrid systems that can give to our scientists the best options to develop their research in the near future. This is because we have already well set a plan for the HPC facilities in the near future, but also because we have in Europe, I would say, a nature enough ecosystem in terms of quantum technologies and quantum computing. We have nice research institutions developing research in quantum computing, as has been said before, but also some companies, some of them have talked today, developing quantum processors, developing software. There's already a big amount of investors willing to invest in this type of companies, and there's more and more users, not only scientists, but also companies that would like to use this technology in the future. So taking into account this, let's say, European map, European framework for HPC systems, and this idea of putting together the quantum systems on the HPC centers, what's happening also is that there are major countries in Europe developing, aligned to this European strategy, national programs. I will go very fast through some of them, but for me, the most interesting thing is to realize that most of them have a lot in common. An holistic vision, including hardware, software, research, facilities, education, training, etc. Pretty ambitious budgets. You have here the 2 billion committed for the German government for a quantum technology plan for this decade. There are also other regional plans, as you can see here. The government of Bavaria, one of the biggest landers in Germany, launching the Munich Quantum Valley project with 300 million euros as the budget. You also have the example of France, almost 2 billion for the next 5 years around quantum technologies. Also Netherlands with also a remarkable amount of money around what's called the Quantum Delta Netherlands program. And also in Spain, we have maybe a not so ambitious plan in terms of budget, but I think it's interesting just to share with you in 2-3 minutes before finishing my talk what we're trying to do in Spain, because at the end is more or less the same that we're trying to do in all the European countries. For me, the main virtue of these national programs is its holistic vision. So we consider here the need to develop quantum computing technologies. So at the end, to acquire and install and operate a system near the National HPC Center. Also, on the second pillar, how to establish an easy way for the researchers to access to these systems. But we have to talk also about research, how to develop new algorithms, etc. And of course, training, education, talent as one of the 4 pillars of these programs, if the main objective of this program is to boost your national quantum computing ecosystem. Just a very quick, we are talking about developing and acquiring computer based, in this case, on qubit superconductors technology. Also, we are planning to acquire small simulators on the National Supercomputing Center, but also around regional computing centers we have, just in order to put in place different type of computing systems. We'll put in place also through the Spanish Supercomputing Network a way for our researchers to access to all these systems. This is very important. The Spanish Supercomputing Network, on the same way that the PRAISE, which is the European network, has been working very well for the last 15 years. It guarantees the access to the national systems for any Spanish researcher that needs to use one of these facilities. So let's do the same with the quantum systems, where the systems, computer simulators will be in place, fully operative. We also will develop, as I've been saying, one of the pillars regarding research. So agreeing with the most important research centers and universities in the country to develop new algorithms, focus in this case on artificial intelligence, just in order to use these future systems when they will be in place. And last but not least, is absolutely mandatory to put in place a program around talent, training, education, etc. Because I repeat it, if you want to boost your national ecosystems, you need more activities like this. I'd like to emphasize the holistic idea for this program. So including systems hosted by the National HPC Center, access to the system, research on algorithms, training, education. And it is something that you can find in all the national quantum computing initiative at European level, always being organized around the national HPC centers. Maybe you have different magnitude in terms of ambition and of course budget, but at the end it's more or less the same everywhere in Europe. And this is my last slide here. So just as brief conclusions before some questions and answers. My main idea, my first idea is that I think it's been clear that the idea of this European technological sovereignty will be one of the main political trends in Europe for the next years. And it opens us some good opportunities in terms of developing science and technology in quantum technologies, in quantum computing, for instance. The second idea is that nobody doubts today the necessary convergence among HPC and quantum computing. At least the European strategy in quantum computing will be fully connected and aligned with the HPC plan, with the HPC strategy. The third idea is that we can consider pretty ambitious some of the major European initiatives in place, most of them following this holistic approach in terms of hardware, software, training, etc. And last but not least, well, I think all these elements will make Europe a pretty good place to develop quantum computing projects in the following years. And with these brief conclusions, I just finish my intervention. Thank you for your attention. And of course, José Ignacio, I'm at your disposal for any question you have. I think I've been pretty punctual, finishing at 11 Spanish time. Thank you very much.
Thank you, Pep. Very nice. May I finish with one question? Okay. Which is, how do you see the collaboration between HPC centers in Europe with those in Asia?
This is a very interesting question because traditionally, of course, we've had more relationship in terms of science, in terms of HPC resources, being honest, with the States, of course. For tradition, for historical reasons, because probably most of our people have spent some of the time in the States and vice versa, etc. But I think more and more there have been new collaborations with Asia in terms of HPC. I don't fully know what's happening in all the countries there, but I've seen in the last years some of very interesting initiatives in some Asian countries. And I know that European Commission is fully committed to a stronger HPC collaboration with Asia. So, well, I can forecast that on the next few years, this will be also a trend, because I think we have to be fully compatible, this need for every country or territory to work on its own sovereignty in terms of technology, with having a fully open scientific ecosystem where the cooperation with other countries or continents are absolutely mandatory if we want to really make progress. So I think there will happen interesting things in the next years in terms of cooperation between HPC centers in Asia and Europe, for sure.
Thank you very much, Pep. We hope to see you here. Okay.
Thank you very much.
Let me thank all the people online, and And come to us if you want to talk about quantum computing. Okay. Thank you very much. Bye-bye.